Alright, welcome to another AQA A-Level Chemistry video. I'm back, baby. I'm back. Yeah, it's been quite a bit of time. I finished my medical interviews now, so hopefully that went well, you know. So yeah, I've missed out on quite a bit now. I know I've been gone for quite a bit. So I know people like probably watching this video saying, bro, when did you even arrive, bro? No one knows who you are from. It's like my first video watching you, man. Like, but stop waffling, man. Just do the video, man. I watched. I looked at the thumbnail and the title of this video, thinking you're serious, fam. Just go with the video. But I will go onto video. Today I'm going to be doing a video on the Arrhenius equation, and I will be talking about. I will actually also cover up on something that I said on a previous video that I want to actually talk about as well. And then towards the end of the video, I'll be doing a couple of exam style questions. And yeah, that's pretty much it. Yeah, it's been a long time since I've done this, so I'll go on to that. But anyway, so before I start that, I'm going to talk about this, a quick note from the previous video, and it's to do with orders. Now, I can't believe I didn't actually mention this because this is such a big thing with rate equations, and that's to do with understanding graphs that represent orders. Now, it's not just about doing. I've already said how to calculate orders and also doing rate equations, but I didn't mention some of the graphs that are used to explain rate equations. Now, these are important because these actually come up in your exams where they might be like a 1 mark question saying, what does this graph represent, or which type of order does this graph represent? You could get those type of questions. But you could get also like a 2 mark or so 2 part or 3 part question that may lead to like a 5 mark question later on. And that's by just, and you may need to understand what the graph represents in order to help you with your understanding of how to answer the question. And what I mean by that is they may want you to use your understanding of orders to help you answer the question, where they don't actually specifically state the order of the reaction, but they give you the graph and they expect you to look at the graph and understand by, they expect you to use your understanding of what the graph represents and what order it represents in order to allow you to answer the question. So if you needed to know that a specific type of reaction is a specific type of order, but it doesn't specifically state, but it gives you a graph. You say, oh, actually, I recognize that graph. That graph would represent something that's of first order or second order, for example, or either one of two. Let's just say second order. It's like, okay, now that I know that this graph represents second order, and the example that is given is for this type of reaction, I can now use that information to help me answer the rest of the question. So that's what I mean by it's very important that you understand what these graphs represent. And yeah, I'll go through it. So the very first one here is first order. Now, a graph with direct proportion, a straight line of direct proportion, is a graph that represents first order. See, straight line. Sorry, I know it maybe. I probably should have done a better job with this actually. That's actually a bit of a butchered line. Let me get a better graph for you. Better line. It's that's probably is it better? Probably a little bit better. I don't know. But anyway, yeah. So because the reason why I want you to think about it like this is because the reason why it's so easy to remember this is because if you understand maths and you understand algebra, think about like what orders. Think about how orders are represented. Remember what I taught in this video about how orders are represented. They're represented as powers. Orders are represented as powers when you to even here technically, right? It's it's technically to the power of 1, but we don't write in maths. Don't really write power of 1. It's just something that we don't usually do. But this is when talking about first order or an order of 1. It means technically x to the power of 1, because we represent the order by the power. Now coming on to the next part. Now I'm going to use an example, right? If a reaction is of second order, for example, I've got the decomposition of NO2 into nitrous oxide. So decomposition of NO2 into NO. so nitrous dioxide to nitrous oxide, that's a second order reaction. And if I use that same principle from before, remember we represent our orders by our powers, x to the power of 2. In maths, we know that when you square something, it's an exponential, and it's a simple, not like a cubic exponential, a squared exponential. It's just, it starts off kind of slow here and it rapidly increases in an exponential manner, going upwards, right? So the higher the value, the higher the rate of the reaction. So in this case, the value that we're talking about here is time. So in NO2 here, so the more NO2 that gets used, this is a decomposition reaction, so it wouldn't be forming, it would be breaking something down. So the more, as time progresses, the more NO2 uses that gets used up. Sorry. As time progresses, the faster the rate of NO2 getting used up. That's the best way I could say, yeah. So as you can see here, the rate of reaction is constantly increasing until you get to this point here where it's arguably at its, or it's not arguably, it is at its highest rate at that specific time there. So in second order, it's an exponential curve. As time progresses, the faster the rate of NO2 being used up. And this reaction represents a second order. Now, the last one is what you think it would be. Remember, so if we're following the same principle of this algebraic understanding, x to the power of 0, x power anything to the power of 0 is always 1, right? It's not increasing, it's not decreasing. It's just, it just is what it is here. So, flat line, nothing that's really going on here. Well, think about what zero order actually represents. Now, the reaction between H2 and CO2 is considered to be zero order. So this doesn't affect the rate. There's no change to the rate of reaction. Remember when we're talking about orders, we're talking about how it affects the rate of reaction. And there's no, this part here isn't part of any types of rate determining steps. I.e. what it means by this is that there's maybe another type of reaction that that may allow it to form the products that you would want, right? But this in itself has no effect on the rate of the reaction, and it wouldn't be part of a rate determining step, and has zero order. So it's just a flat line, just like that, just standard flat line. Okay, now that I've covered that up, hopefully this made sense and I wasn't waffling too much. The description of this video explains why I waffle a little bit too much. Is my retainers makes it difficult for me to speak sometimes, but I'm not going to make too much excuses for myself. I'm just going to go straight back into this video here and continue where I left off. But again, if you didn't understand that, or if I didn't explain it in a way that made it helpful for you, if I confused you, leave a comment in this video and I'll try to explain it in a way that makes a bit more sense to you, and I can help you a bit better. But yeah, I'm going to continue with this video. So the rate constant can be expressed in terms of activation energy by using something called an Arrhenius equation. So I'm going to be going through what the Arrhenius equation is, why it's useful, how it can be rearranged, as well as why it's so commonly used when doing rate equations. And yeah, I'm going to go straight into it. And at the end of this, there'll be some exam style questions at the end. So the Arrhenius equation. The Arrhenius equation is this. This equation is what we understand as the Arrhenius equation. And that's K is equal to AE to the power of minus EA over RT. Right? So this is given to you in your exam. But if you're looking at this thing, actually, you know what? Oh, there's no teachers here. If you're looking at this and you're saying, fucking hell, I'm not doing that shit again. Like, I'm not gonna remember that. You don't have to remember it. But what I will say to you is that the more time, I've always said this constantly, if you want to understand the topic, you got to do the exam side questions. There's no point saying to yourself, I understand the content so well, I can just do well in an exam. You got to do more exam side questions. And the more exam side questions you do, the more common, the more second nature some of these equations become to you. You probably know a couple of examples of equations that you don't actually need to know for your exam, but because you've done them so many times, you can just memorize them off the top of your head. And this is just one of those equations that the more time you do them, the more easier it is to remember them. It's like kind of concentrate, or you actually need to know concentration the relation to concentration equals moles over volume. You need to know that off by heart. But say that was given to you in your exam, I wouldn't have to look at it. I just know that off by heart. Yeah, this is one of these ones, and you have there are some times where you have to rearrange this equation to find something else. And again, if you done this type of question so many times, you don't even need to work out how to rearrange it. You just remember what the rearranged version of it is. So what I'm gonna say is that I'll leave some exam styled questions at the end, but you should do some more in your own free time, and you'll be able to do these types of questions really, really easily and really, really quickly. So yeah, but I should probably explain what these letters and so what these values are representing. So in this equation, K is the rate constant, which I picked up on the previous video when I was talking about rate equation. A is called the Arrhenius constant. I forgot what the exact constant is, but I remember doing it. I know it's time. I think it's 2.27 times 10 to the power of 10. Doesn't matter. You're not gonna. They give that to you in your exam. I was just thinking about off the top of my head if I can remember it, but it's been some time since I've done some of these questions. But either way, the Arrhenius equation is the Arrhenius constant is given to you in your exam, and that's a specific value. R is the gas constant 8.31, as you know. T is the temperature. So this is a power here. Some people think that this is minus EA to the power of RT. No, it's to the power of AE to the power of minus EA over RT. This is a power here, right? So just want to bear that in mind. So R is the gas constant, which you should be aware of from the gas equation. PV is equal to nRT. Temperature T is temperature, and then EA, as you will definitely be aware of, is the activation energy. And that's about how it's not just about knowing the equation, it's about how you can use it. Now, using the Arrhenius equation. So the Arrhenius equation lets us find out why it's so important, because it allows us to find the rate constant at different temperatures. More importantly, if we measure the rate constant at a bunch of different temperatures, we can then calculate the activation energy. So you should be aware from the previous video when I was talking about the rate constants, rate equations, you should know that K is actually temperature dependent. So the rate constant is temperature dependent, which makes sense, obviously, because the rate of the reaction would be higher if the temperature was higher, because you have more particles have the activation have sorry more particles have the energy greater than the activation energy to successfully collide and react, right? But this equation just allows us to work out the rate equation, the rate constant at different temperatures. But more importantly, if we already know the rate constant, the A, and as well as other values, we can actually rearrange this equation to work out the activation energy. I just forgot to mention, if you don't do maths and you're surprised, what's this E value here? E is something that you learn in maths. Especially when it comes to exponentials, it's called Euler's constant. Don't worry about too much, because people might get confused. I don't know what the hell's going on there. Don't worry, it's something that's in your calculator. It's a constant. It's kind of like a large value like pi. But E is used for exponentials. And if you struggle to rearranging E is not like how you rearrange other values. But don't worry, if you don't know how to rearrange using E, not a problem. All you need to do is just memorize certain equations and you'll be splendid. You'll be fine. Don't worry. But yeah, but just in case you looked at that E and said, what the hell is that all about? But yeah, but anyway, as I said before, this is important because we can work out K, but we can also use it to work out EA, or we can use it to work out the temperature in itself. You can rearrange it in many different ways here, but that's why this equation is so useful here. So there's a couple of key factors surrounding the equation. As the activation energy rises, the rate constant gets smaller, so the rate is slower. And this is what you'd expect, because if you think back to the Maxwell-Boltzmann distribution, the higher the activation energy, it means that there'll be fewer number of molecules with enough energy to react. So the key point we're trying to get here is that if the activation energy rises, that means that there's a higher energy requirement that needs to be reached in order for those compounds or those particles to successfully collide and react, which means that there's now a lower number of particles with energy greater than the activation energy to successfully collide and react. Hopefully you're following up with me. If you're not, leave a comment in the description. I can always thing about talking a bit slower if you're not catching up with me. But hopefully what I'm saying is making sense to you. I'm just talking about things that you should know from year one in terms of activation energy, the number of particles that have energy that's greater than the activation energy to successfully collide and react, right? So all I'm saying here, if I was to represent this in graphical terms, if the activation energy was here at the green, where the green arrow was, where the green line is, that means that there's a greater number of particles. So everything right of the green arrow here, of the green line here, is the number of particles that have energy greater than the activation energy to successfully collide and react. But if I was to move that activation, if we had a higher activation energy, right? If we had a higher activation energy, and I move that here, we've now decreased anything that's here wasn't going to be is not part of, is not doesn't have, sorry, anything that's here means that we have particles that don't have enough energy to successfully collide and react. It's only from the yellow line right now. So we've now reduced the number of particles that have energy greater than the activation energy to successfully collide and react, which means that if there's less particles of energy greater than the activation energy to successfully collide and react, which means that it will mean that our rate of reaction is slower because we have less of those types of particles, or there's less particles with that energy. I'm gonna stop saying energy greater than the activation energy to react because it's kind of long. You can in your exam you can literally just represent it by like this. In the maths term, that exactly means what I just said. It just means that energy that a particle has, because energy can be represented by E. J is usually is a unit. Don't think that J is representing E. E represents energy. J is the unit used. J represents joules, which means which is the unit used to measure energy. As just some people get confused between that. I just wanted to clear that up. But yeah, this in maths term, this is just what I said here. Energy is greater than the energy of the activation energy. So energy is greater than the activation energy. There you go. But as bringing it back to this point here, so if we just keep on moving this this arrow here, so we keep moving the activation energy line, we see have less particles with the activation energy, less particles with E greater than the EA, and we just keep on going and we keep on going here. So as temperature rises, the rate constant gets larger, so the rate is faster. Right? It's because remember it's temperature dependent. So these are things that this is important because we have to understand. If you understand the Maxwell-Boltzmann distribution curve, this is no problem to you. I made a video on Maxwell-Boltzmann distribution. If you want to go back on that, I'll try to remember to leave a link in the description to that video. But yeah, if we're just talking about just by itself alone, having a high activation energy would decrease the rate of reaction. However, if temperature was to rise, we know that this graph would actually shift. This graph would be more like I'm gonna try and do this first time. Nope. That's way too crazy. Right, it's not perfect, but you get the no. I want to do it better. I could definitely do it better. Yeah, yeah. So if temperature was to rise, this graph shifts a little bit to the right, and we found ourselves that this activation energy curve here. So let's say the yellow one or the orange one was, we can have still a high activation energy, but we now see that there's if I was to continue this line going upwards now, we have more particles. If I keep that same line there, we still have more particles with activation energy to successfully collide and react. Because we've increased temperature, we've actually shifted our graph to the right. And remember, the area underneath the graph is the area underneath the graph represents the total number of those molecules, the total number of molecules. So by increasing the temperature, we make it shift to the right a little bit. And that's what we mean by rate constant, because remember what the rate constant represents, right? But if we're now increasing that temperature, we're increasing the particles with activation energy to successfully number of particles with the energy greater than the activation energy to successfully collide and react, and therefore will increase the rate of reaction, that rate constant would now increase. And yeah, and this could also be represented by the Maxwell-Boltzmann distribution. But the Arrhenius plot. So an Arrhenius plot is a name given to the graph used to find the activation energy. The activation energy, you can rearrange the Arrhenius plot to find the activation energy. Now, I'm not going to do the whole Arrhenius plot thing, but what I will do is the Arrhenius equation, right? Do I actually have the... Wait, let me see if I have the Arrhenius plot. Oh, no, I will do an Arrhenius plot. My bad. I will do an Arrhenius plot. I do have one in me on this video. Yeah, I will go through, because in fact, you have to actually do an Arrhenius plot for your exam. So I thought it was a completely different thing. My bad. You actually have to do an Arrhenius plot for your exams, and it's not as difficult. It's not a difficult thing to do. Just plotting a normal graph. It's just about understanding how to get the values, and I'll explain that here. So the Arrhenius equation, as we understand it, is this. It can also be rearranged into this. Now, if you have no idea how I've got to this here, don't worry, I'll explain how to do it. If you are very good with maths, I did A-level maths, so I kind of know how to do this already, but you can understand where I'm coming from with this. And the reason why we're getting natural logs is because of that E. Now, I'm going to explain how to actually get from this to this. But then again, as I said before, if you don't know how to rearrange equations because you didn't do A-level maths, don't worry, you can just remember this equation here, and just remember this equation, and you can just rearrange. If you want to work at the activation energy from here, you can just rearrange this equation like you normally would. At this point, you can just normally rearrange the equation, and it would be fine. But I will explain it just for the sake of, I'm going to stop talking now. Anyway, so the equation is K is equal to A e to the power of minus EA over RT. Now, because of this E here, we have to do something called the natural log, right? And that would mean doing ln K. This is how we get rid of the natural log. We have to do ln K is equal to ln times by A e to the power of minus EA over RT. Now, what this can also what you have to understand here when you're doing natural. I'm not going to do a video on natural logs because there's probably some better maths teachers that can explain it to you. I'm not really bothered on doing that right now. But what I would just say is that if you know natural logs, you can represent. When you time something with natural logs, it's the same as doing. It's the same as actually adding it. So it's the same as doing ln A plus ln E to the power of minus EA over RT. Now in maths, ln E, if you actually type it into a calculator, is actually just 1. So ln E, we can just cancel that out again. Ln K now is equal to ln A, and it's equal to 1, and your power just drops down to the base. So now it's no longer ln E to the power of minus E over RT. It's just plus or minus EA over RT. So that part of there, I can just put that over to the other side now. Ln K is equal to minus EA over RT plus ln A. Or you could just I could remove this here. Ln K is equal to ln A minus EA over RT. Or if I want to put it like that, ln K is equal to minus EA over RT plus ln A. I only did this, now I did this very quick and shorthand because I know some people, this is for people that know how to rearrange, but they understand what's going on, but they just kind of didn't understand how to get from here to here. Now, for people that have no idea what's going on because they didn't do A-level maths, watch a video on natural logs, and that might help you out. But then again, I don't think it's ever good. They never really have a question of you rearranging this because they know some people don't do A-level maths, so I don't worry about that too much. Just know that if you this equation here and this equation here are all that you need, and there's another rearrangement, but the other rearrangement is what you'd expect. I'm going to go into that later. I will go on to that later about how to rearrange to find the activation energy. That is something that you would be expected to do by yourself. But yeah, this is the two equations that they'll use for you. The reason why this equation is so useful is what I'm going to go on to next, is that this means that if we plot the graph, which is the plot of the graph that we said I was going to talk about before, the Arrhenius plot graph, this means that if we plot the graph of ln k against 1 over t, you can have a graph for a gradient of as, because I can actually represent this as, can you actually see later on? Oh, it doesn't mention it. Anyway, I'll just represent it myself. This graph actually, oh yeah, I have it here. Sorry, I have it in my little journal that I have here. If you look closely, if we can use it, we can actually use this as an equation, as in y is equal to, this is why I prefer writing it like this instead of writing it like this. And the reason why is because we're actually going to use this as an equation. And if I was to dumb it down here, y is equal to mx plus c. So if you're struggling to see the mx part, the x here is actually represented by 1 over t. And it's actually, I'll separate it out again. So ln k is equal to minus EA over R times by 1 over t plus ln A. Ln k is equal to y. The minus EA over R is your m. 1 over t is your x. And then your ln A is your plus c. Sorry, I had to just do something quickly. All right, and now if we know that this can be used as a graph, this means we can use the graph of ln k against 1 over t, and you can use your and you have a graph with the gradient as m. Remember, m would be representing minus EA over R. And now we can plot a graph. We have our y, we have our m, we have our x, and our plus c. The plus c we can work out anyway by just plotting the graph. We can see where that is, but our c will represent ln A. And you'll find that that value is always interceded, because A is actually it's a constant. Sorry, I had to shuffle things a couple over here, but I'll just continue on. So I'm not going to go through reading in this exact example here, but this is example of the type of graph that they'll give you. So they'll give you a range of values here, and all you have to do is just fill in the couple plots here, and this allows you to create your table of values. Now, this is very easy to do. I remember when I first done this, I had no idea what I was doing here, and all it is, this value here is just 1 over this. I didn't know, it's just that simple. It's just 1 over 286 is equal to 3.5, or 3, it's technically 3.49, but it rounds it up. But 3.5 times 10 to the power minus 3. And if you want to work out this, just do 1 over 302. Just literally just follow this, and you'll be fine. 1 over 302. 3.31 times 10 to the power minus 3. And then for the ln, it's literally the exact same thing. It's literally just telling you here, but it's literally this value here is 1 over t. Just do the ln value of that. So ln. So we already know that this is already in the form of 1 over t. Just do ln in your calculator of 3.7. You'll find the ln button right to the right of the logarithm button. Or if you have a Casio FX 991 EX, which is the one that's basically the white calculator that you see in the shop, with the A-level white calculator. In case you didn't know, I'm just reading what it says on the actual calculator. But if you have that model, it's actually just the one. You'll find the ln button on the second row of the black keys, and it'll be at the very end of that second row. next to logarithm to, yeah, and that's where it is. But yeah, so ln of 3.7 times 10 to the power of minus 2, and that's 3.29, or technically minus 3.3 because it's minus 3.2968. So minus 3.30, and that is literally, that's your 2 marks there, just for doing that. Easiest 2 marks you'll ever have to do in the exam. You should just put in a couple numbers into a calculator, right? And now you use this information. You have your 1 over t is your x-axis, and your ln k is your y-axis, and just using these values here, using this value here and this value here. I make a mistake. It's not actually. It's not 1 over t. It's ln 1 over t. Let me use my. The reason why you can just use 1 over t. I also make it clear. You can just use 1 over t. There's no problem with using 1 over t. 1 over t and ln 1 over t are still represented by. They can use either or when it comes to your x-axis. The reason is because 1 over t is such a small value, you can't easily distinguish between 1.85 times 10 to the power minus 2 and 3.7 times 10 to the power minus 2. They're very, very small, and on a graph be very, very kind of difficult. So we just used the natural logarithm of those numbers, so it makes it easier for us to put them on the plot. There's no like, it's just in case this might confuse you. These either or can be used. We just use the natural logarithm of it because it makes it easier to separate them out and use on the graph. And then you plot out your graph. There might be a couple outliers like this, so don't worry about that. They may even ask you a question on why they're just saying that. It's just mentioning, using a bit of your understanding of basic statistics, saying that that's an outlier, and that could be because of and then again they're testing your investigative skills, because in the practical you say to yourself, maybe there was an irregularity in the way that we perform the practical. Like this, I'm saying this because this might be something they ask in the exam. They say, why is there an irregularity in this value here, or why may there be any anomalies? You might get anomalous results, and that's because during this practical, because remember you're doing it. This is a rate of reaction practical. So if you may be testing the rates of reaction to do with a decomposition reaction where you have to use a calorimeter, think about the examples with the calorimeter, right? Because that's a perfect example where you could use this type of equation, right? Is it a perfect example? It's one of the examples. But yeah, think back to your investigators of saying that maybe we didn't use the right type of it's probably a better example. Probably let's say iodine. It'll be like an iodine clock test. Yeah, iodine clock test is probably a better test. But same probably some people had different reaction times, so we could have used the same person to use the stop clock, or maybe we didn't make sure that we didn't add the same concentration every time. So instead of using 1 drop and 2 drop, which isn't very accurate, we could say we added 5 milliliters specifically of for every drop, and that could be much more. That can improve your accuracy. Just stating things like that. This is these things that they can ask you whilst you're doing after you've done your graph, and just by being aware of that. So, for example, and here, the as long as you get the right plots, like I've got 3 plots here that are roughly correct, and then some of them might be slightly off, but that's fine. You'd have to do you'd have to do a, what's it called again, the line of best fit. That's it. A line of best fit. Once you've plotted down your units, and it should roughly be in a line like this, and that's all it is. That's sorry, that's nearly everything you have to do after doing the graph. After you've done the graph, that's nearly everything. The last thing they have to do now is to draw a gradient, or to calculate the gradient. Just let's say, for example, this gradient here. Now, this is the part where everyone gets confused. Everyone makes a mistake. Now, they may ask a question here saying, how do you work out the activation energy of this example here? Now, the gradient, we know that if we work out from this using, rise over run, we know the gradient of this graph is minus 5.747. This is random example, random example, right? But let's just say it's that's the gradient of this graph. But that doesn't necessarily mean that that's what the activation energy means, because people forget the M is minus EA over R. So the gradient of the graph is equal to, so M in this case, if it was minus 5.7, what's it called? Minus 5.747. It's not equal to 47.9, is it? Yeah, that probably sounds like a wrong value. But anyway, I'll just do it here quickly. Should I use it here? I'll do it here. I'll just do it here, and then I can just erase it anyway. M is equal to minus EA over R, right? So that means that EA, or the activation energy itself, is equal to minus M multiplied by R, and that's equal to the activation energy. So minus is minus and minus, so minus 5 point, which makes sense because we're going to get a positive value for our energy. Minus 5.747 multiplied by our value for R, which is 8.31 always. That's our R is 8.31. So I just take away that R there and just put times by 8.31 would equal our activation energy. I don't think it's 47.9, but that sounds completely wrong. So 5.747 or minus 5.747 times by 8.31. Yeah, not too, there's a bit of an irregularity there, but it's 47.757. But if it's just three significant figures, if they tell you that, or if you you usually look at the lowest amount of values that you have, and 8.31, they would give you the amount of significant figures in your R. So if it's just 8.31, the lowest number of significant figures is 3, so 47.8. So convert, here we go. And that's joules. This is kilojoules per mole. Kilojoules per mole. Yeah. Depends what, if you're using 8.31, that's in, yeah, kilojoules per mole. And that's literally it when it comes to working out the EA from this specific example. Now, you need to be able to calculate the activation energy given the rate constant and vice versa. So this example here was used in the graph, but you also need to be able to work out the activation energy just straight from the example without having a graph. And that's by just rearranging this. Now, the Arrhenius equation, calculating the activation energy. The Arrhenius equation is, as we said before, K is equal to AE to the power of minus EA over RT. But if you want to calculate the activation energy, the easiest way is to rearrange the equation into this here. Now, if we rearrange the equation into this here, we can just rearrange it as you normally would. So I'm going to use this space here. Yeah, I'm going to just, I'll use this example here. I'm going to, why can't I move any of this? Doesn't matter. Anyway, why is it acting up pretty slowly? There we go. Anyway, that's a bit weird. Sorry about that. So I'm gonna go back to this example here. So it's ln K. Weird. Ln K is equal to minus EA over RT plus ln A. And now we're just rearranging this equation so we could just get just EA. Now the first thing I would do here is move the ln A over to the left. So the ln A to the left. So ln K minus ln A equals to minus EA over RT. Again, you should be able to rearrange equations. Bring the RT over. So RT, so I have to multiply both sides by RT to get rid of the RT on the denominator side or of the right hand side of the equation. So RT is equal to ln K minus ln A, but that's equal to minus EA. So I have to minus RT, because we can remove the minus part. Minus RT is equal to ln K minus ln A, and that's now equal to your activation energy. And now if you put all of this in, your 8.31 times by your temperature times by ln K. Remember, it's ln K. Some people forget. You have to do the ln version of your K, and sometimes they'll give it to you in your ln version, but you forget to see they're giving it to you in your. They may actually give a table of values where they leave it in the ln value, but you forget they've done it, so you do ln over ln. So just be wary of what you're typing into your calculator. Sometimes you don't have to sometimes you don't have to put it in the ln form. Sometimes you have to put it in the ln form. But just be wary of what you're putting into your calculator. If they've given it to you as it is, then you don't have to worry. But just no, first just being wary here of what type of equation you're forming. That's number one. Once you formed your equation, it's just about not being silly and stupid and just putting in the wrong value after doing all this hard work of rearranging your equation. And that's, once you got to that point, you've done it. You've now rearranged your equation, and you can substitute in the values for K and A that you're given to get the activation energy out. And you can calculate the rate constant. To calculate the rate constant, you can just use the Arrhenius equation and throw all of the values into your calculator. So if they just want you to work out this, you just throw in all the values into the calculator. But yeah, that's it. That's the end of this video. Now I'm going to be doing the exam questions now. There's an 18-mark questions here. Now, if you want to take a break after listening to me talk all the time, I get it. But I've got some exam questions here for you. 18 marks worth of exam questions. So the initial rate of reaction between compounds A and B. I'm going to read out the question, but I'm just going to show it to you all here. That's 18 marks worth of questions. And pause the video now, and I'll try and answer them after this video. So after you say, oh, we're talking about. Pause the video now and try and answer the questions, and then I'll go into it. Alright, so hopefully you had enough time to go and read over those questions and do the questions. I'm now going to set a timer and then try and do that myself. So if I just go to here, set one on my watch as well. Okay, so the initial rate of the reaction between compounds A and B was measured in a series of experiments at a fixed temperature. The following rate equation was deduced as R is equal to KAB squared. So they've actually given it to you here. So they've already given you the rate equation. Using the data for experiment 1, calculate a value for. So if you want you to complete, so you complete the table of data below for reaction between A and B. So you want me to complete the table, fine. And then part 2 of the question is, okay, I need to work out the rate equation though. Using data for experiment 1, calculate value for rate. Okay, in this one example here, I'd actually advise doing the part 2 to the question first, because you actually need the rate equation in order to answer part 1. So I don't know why they've done it like that, but you need to actually use the rate equation to actually answer this question. So yeah, I do the part 2 to this question first. So want to work out K. So K is equal to R over AB squared. R over A times by B squared. So then, okay, don't give you, they usually give you enough space in the actual exam. I don't know why they haven't done it here, but that's fine. 10.4 times 10 to the power of minus 3. I don't know why they do. Index form, standard form is usually, you wouldn't be 10, it would be 1 point. It doesn't matter anyway. You wouldn't usually write standard form like this, but it doesn't matter. So just use what they give you. Use what they give you in the real thing. 4.80 times 10 to the power minus 2. 6.60 times 10 to the power minus 2. So 6.60 times 10 to the power of minus 2 squared. All of that's under that equals, as I said, in the real thing, they give you much more space to answer a question like this. 10.4, just put that into a calculator now, times 10 to the power of minus 3 all over 4.8 times 10 to the power of minus 2, I don't know, 6.6 times 10 to the power of minus 2, and then it's squared. 49.7. Now, I'm not meant to spend too much time on this question simply because of it's just this part here will be a 2 marker in this particular part. So I can just see from here, it's moles per dm, this part is moles per dm cubed. That's moles per dm cubed per second. This is the numerator, right? And this is moles squared dm to the power of minus 6, but it's on the denominator side. So those basically cancel out, leaving you with the s on the top. I'm not going to spend too much time on this one, but because I'm just trying to do this under timed conditions, but hopefully you can see it. If you don't see it, then let me know in the comments. I'm trying to answer it, specifically go through that again. And then we're just left with this, because we've already cancelled out this part here and this part here. We're just left with moles squared dm to the power of minus 6. Bring that over to the numerator side, right? Now it's moles to the power of minus 2 dm to the power of 6 per second. Now I can fill out the rest of this now. I'm not going to spend too much time writing out every single question, but we already know what it is. So 49.7 times by 4.8 times 10 to the power of minus 2 times by 3.3 times 10 to the power of minus 2 squared. This should be 2.6 times 10 to the power of minus 3. Oh. And for the A, R over KB squared. (5.2 times 10 to the power of minus 3, 49.7. So over 49.7 times by 13.2 times 10 to the power of minus 2 squared. 13.2 times 10 of minus 2. I got 6.0 times 10 to the power of minus 3, so 6.00 times 10 to the power of minus 3. And then the B would be the square root of R over K times by A. Here, it's just about knowing how to rearrange your equations, so it shouldn't be too difficult for you. 10.4 times 10 to the power of minus 3 all over 49.7 multiplied by 1.6 times 10 to the power of minus 2. 1.14 times 10 to the power of 1.14 times 10 to the power of minus 1. Yeah. Alright, cool. I'll try and pick up the pace now. Yeah, okay, I spent exactly 6 minutes on a question anyway. State how the value of the rate constant K would change if at all, if the concentration of A were increased in a series of experiments. Concentration would be no change. It's temperature dependent. K is temperature dependent. The rate of reaction probably change, but K will be temperature dependent. In another experiment, the effective temperature on the rate of reaction is investigated here, Complete the table above, no problem. 1 over 318. Easiest marks you'll get in the entire exam. So that's, just leave it in the way that they want it. 0.00314. And then ln 6.63 times 10 to the power of minus 7 minus 14.2 minus 14.2. If the Arrhenius equation can be written in the form of that, use the data in the table above to plot a graph of ln K against 1 over T on the grid in figure 2. Calculate the activation energy EA, okay, in kilojoules per mole. Okay, so we write. Okay, so we make our graph and we use our understanding of the equation to help us calculate the activation energy. Okay, that's fine. So I'm just plotting the graph. So action can go for one. So minus 13.6. So minus 13. Minus 13. 14. 15. No. 14, 15, 16, 17. And that's 18. 0. Minus 14.0. Minus 15.0. Minus 16.0. Minus 17.0. Minus 18.0. So minus 13.6 and so 14.2 and 314. $14.9 319 to 14. $16.3 330. That's a terrible. Sorry about that. Sorry about this. This is time wasting right now. I'm sorry. That's just I aim to be quick about that. I'm sorry about that. 17.7 341. 17.7 17.7 17.7 341. Now just draw a line of best fit. So I'm using a ruler right now to try and draw this graph on my iPad. Yes. Yeah. I think my ruler's off. I think my ruler's got jagged ends to it because it doesn't look straight. Anyway, I'm not gonna waste time on that. Use a proper ruler in the exam so it doesn't. My ruler I think is a bit off. You know what? That's the best I could do. Anyway, we work out the M. M is equal to minus EA over R don't want to waste any more time really with that. Because we only got 6 minutes left, and I might need that for the rest of my okay. If we know that, so I cut the m. M is equal to minus 17.7. Let's just use the graph here. This point here. So that'll be a rise. Minus 13.6 over 3.41 times 10 to the power of minus 3 minus 3.40 times 3.10, sorry, times 10 to the power of minus 3. Sorry, I'm really butchering this. I should be much faster than this. Alright then, so minus 17.7 plus 13.6, same thing as that, over 3.41 times 10 to the power of minus 3 minus 3.10 times 10 to the power of minus 3. Okay, so our value for m is minus 13,225.8, really. Right? So now we know that's the m, but to work out the EA, so that's minus 13,225.8. EA is equal to minus m multiplied by r. So EA is equal to minus that, which makes it positive, times by 8.31. And then activation energy is equal to 109,906 joules per mole. Activation energy is now 109.9 kilojoules per mole. They use three significant figures, don't they? I'd say 110 kilojoules per mole because they use three significant figures. Anyway, I'm wasting time now. So, the rate constant K for a reaction vessel with temperature shown by the equation is shown there. They give you all the values there. Calculate value for the Arrhenius constant A for this type of reaction. Okay, so I'm just rearranging this equation to get A. So, A is equal to K over e to the power of minus EA over RT. So then, and I think they've given you everything. Yeah, they've given you everything to work out A. So A is equal to, 3.46 times 10 to the power minus 8. 3.46 times 10 to the power of minus 8 over e to the power of minus 90. Yeah, I used 96,200. So minus 96,200 over 8.31. And what's the temperature that we have? Temperature is 25 degrees Celsius, but we're using Kelvin here, so that's 298 Kelvin. Again, you just remember that from just doing lots of questions, and then you get your answer is equal to, so 3.46 times 10 to the power of minus 8 over Euler's constant minus 96,200 over 8.31 times by 298. Like around that 2.57 times 10, rounded to 2.57 times 10 to the power of 10, I believe. Yes. 2.57 times 10 to the power of 10. How much time have I got left? Okay, so K is just, the K is just in seconds over e to the power of joules over joules per Kelvin per mole times by the Kelvin. So then cancel out the Kelvin, cancel out the joules, the joules per mole. Cancel out that. So the units is just seconds to the power minus 1. That's it. Stop there. Just about in time. Yeah, you should be doing it much faster than barely on time. Let's go to the mark scheme here and compare our where's the first question for this? I remember, I think I used a different question for this one. No, I didn't. Yeah, I did. Was it this one? We'll see. Trial and error. It was this one. Okay, so green pen this. 2.60 times 10 to the power minus 3. 6.00 times 10 to the power of 0.6 times 10 to the power minus 2 is the exact same thing as 6 times 10 to the power minus 3. So don't worry about that. In the exam, we would accept that. And then you wouldn't say 11.4 times 10 to the power minus 2. You could get away with saying 1.14 times 10 to the power minus 1. Equally as fine. They mean the same thing anyway. So you'd get the 3 marks there. Working out the value for K, just doing doing this is fine. Obviously you wouldn't put the circle there. I put this I just put the circle there to help explain to you guys, but that's that. So just this in itself, just doing that as a mark, getting the correct answer is also then another mark. And then getting the right units, moles to the power minus 2, dm to the power 6, s to minus 1, also another mark. 6 marks there, no change, because remember K is temperature dependent. The rate of the reaction would be affected here because it's first order to A, so that would be affecting that, but the rate actual constant is just temperature dependent. So 1 mark there, 7 marks in total there. And then I believe I changed it to a different type of what question is this? It goes into question 9, so question 8. That's correct. And that's correct. That's 2 marks there. So I assume, so you get 1 mark for all points were dotted correctly. Yes. Yeah. Best fit line. Best fit straight line based on the student's data, ignoring anomalous points. Yeah. Yeah, there's only one anomalous point here in this example here, so there. Bear in mind this, I did do this with a ruler. It's just that it's hard to translate that well with this on here, but it would be done with a straight line. So yeah, put it there. Gradient calculated within the range of 12,876 to 13,598. They worked out minus 13,125. My value fits within that range anyway, so I'm fine. Mark is for their gradient times by 8.31. Yes. You would have a negative gradient, by the way. The gradient calculated within that range, just saying within that range, but it is a negative value. It's meant to be. And then the EA has to be within the range of 107 to 114. So that's fine. And that's 5 marks. Yeah. And then the last one, so rearrange it. There's 2 ways you could rearrange it. I'll show the 2 ways that you could rearrange it. But I'm gonna go so. Do I say it to 2 ways? This is, you can see it here anyway. But anyway, the way I've done it is fine. So rearrangement is that's a market for just rearrangement. Correct conversion of both the activation energy and the temperature. So recognizing that this should be 96,200 and this should be 298 instead of 25. That's another mark. Correct answer allow 2.45 times 10 power. Did I do power of 10? It should be to power of 9. I think I was rushing it because I didn't a bit. That's clearly wrong. It's clearly to the power of 9, not to the power of 10. To the power of 9, so I wouldn't have got the mark there. This is why, I mean, if I was doing this proper seriously without trying to explain to you guys, probably I would have clocked in that. But clearly I didn't read my calculator properly. That's my own fault. I apologize for that one. But yeah, I wouldn't have gained the mark for that one. Units, yeah, that's not a problem. And this is a 4-mark question, so 3 out of 4 here. So 17 out of 18 I got there. But the whole point of this is not for me to, I've already got my A-level, so I don't really care about doing well for this. It's just about explaining to you guys how I should have done. And this is just a calculator error for me not recognizing it. Hopefully me explaining this part here, it was calm for you to explain. I had to rush it there, but I'll actually explain this one a bit better if you didn't kind of get what I mean here. So we know, right? We know that it is. I'm just translating this into the units here, right? So our K value for K is just S to the power of -1. That's all we have. And then we have E. Our activation energy is in kilojoules per mole, but we converted ours into joules per mole, right? So joules per mole, so minus joules per mole over kilojoules or joules per Kelvin per mole, joules per Kelvin per mole. Sorry, it's kind of minuscule there. And then times by Kelvin. So if you're doing Kelvin times by Kelvin to the power of -1, those would instantly cancel out, right? And then you have joules per mole here, cancel out. And that's it. Now you're probably thinking, but it's got the E here. It doesn't matter with the E. You can still cancel out. Don't worry about that. I know this is a power. This is not a value underneath. It's a power, but you can still cancel out. So it's not a problem. And yeah, if there's anything that this is my first time back in quite a while. I'll try to keep the consistency up. But if there's anything here that maybe confused you want to say, just comment me in the video and I'll try to correct it. I'm trying to make these videos as best as possible for you guys. But that's it.